Okay, so we'll start the first question with, it will be not difficult. You already saw something similar. So let me see. So first one would be evaluate limit as x goes to -3 of x squared plus x minus 6. And then the bottom, we have x plus 3. All right. Okay. So whenever you see the absolute value, you know exactly that you should start with doing a piecewise function, right? So we would have negative. So let me put that as like f of x, negative side of x squared plus x minus 6 over, well, let's start with just the numerator, right? So that would be easier. So only with the absolute value, and we will have a positive x squared plus x minus 6. Okay. Now I think it would be a good idea if we just actually simplify it here. Maybe that would be even easier. So let's see. We have here x plus 3, right? And x minus 2, and we divide by x plus 3, right? So we can separate. Let me actually move that down or erase that. Maybe we can just simplify it first. So we would have x plus 3, x minus 2, and we divide it by x plus 3. Now, I forgot the limit everywhere. Limit as x approaches -3. And then we also have here limit as x approaches -3. Okay, we can see that we can cancel these two, and we have essentially here limit as x approaches -3 of x minus 2, right? So now in this case, you can just divide it into a piecewise function. We will have negative x minus 2 and positive x minus 2. And in this case, we would have x is less than negative. Oh, actually, yeah, we need to draw the number line, right? To check what we have. Okay, so what's it called? The critical values are here -3 and 2, right? So we need to check here, let's say -4, 0, and 3, right? So the function will be so x squared plus x minus 6. If we plug in -4, so we would have 16 minus 4 minus 6. So that's going to be positive here. At the 0, we have -6, so that's a negative here. And here we don't really, it doesn't really matter because we are only interested in when x approaches -3, right? So we are kind of looking at the values on the left and on the right side of -3. This is not really important in this case. So we see that we have the top function with the minus when x is less than, sorry, great, greater than -3, and x is less than -3, right? So, sorry, what? Okay, so the positive side for this one and the negative side for this one, right? Okay, and then we also know that the function is not defined at -3, right? So we can also add another one, undefined at x equals to -3, or, since we already put just bigger than or less than, it doesn't really matter. We don't necessarily need to write it here. We just know that there's a hole here. Okay, so now let's look at the function from the left side and from the right side, right? So limit as x approaches -3 from the left side is gonna be x minus 2, so that's -3 minus 2, which is -5. And limit as x approaches -3 from the positive side, that's gonna be the first function, right? So that's gonna be -3 minus 2, which is -5, which gives us +5. As you can see, these are not equal, right? So we can say that limit as x approaches -3 of this f of x does not exist, okay? Okay, next problem. If you have any questions, you can stop me anytime to ask.
Professor,
Yes?
can you go over the part with the number line again? The
Ah,
the values that you got?
yeah. Did I make a mistake somewhere?
I don't know. I got -4 when I plugged it in. I got negative for that. -4 minus 2, I got -6.
16? Let me see.
Down a little on the number line.
Okay, so we have -4 squared, that's 16. Then -4, 16 minus 4, that's 12. Minus 6, that's +6, no?
Oh, yeah, I just did it with x minus 2
X minus 2. Minus 2 is here, though.
in the denominator. Or for I just used the absolute value of x minus 2 as the function that I plugged in the -4 to.
Oh, you mean this one?
Yes.
Oh, that's after we, what's it called? Actually, yeah, we simplified that. And now we have this one. Yeah, for this one, if we, let me see. That's a good
Maybe the
question.
denominator also is supposed to be negative on the top one.
All right. Yeah. Okay. All right. Yeah. So if we take this one, right, and we go to this as a limit as -3, right. Yeah. Okay. Let me see. Uh, yeah. Let's redo that one with the just limit x approaches -3 of x minus 2, right? So if we separate it into negative x minus 2 and positive x minus 2, right? And we still have this critical values of -3 and +2, right? So if we plug in, let's say -4 here, we have -4 minus 2, that's negative, and negative, let's say 0. 0 minus 2, that's still negative though, in both cases.
That's what I got, the two
Oh,
negatives.
oh, 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 I see what the problem is. Okay, so we will need to simplify it after. Okay. All right, let me redo that. Okay, so usually what we do, right? We usually start with this function, right? Just for simplicity, we can write it as limit as x approaches -3 of x plus 3. Let's just do like that, right? Or this x minus 2 divide by x plus 3, right? So before we do any simplification, let me actually move that down a bit. So this is our original function. So now we need to break it down into pieces, right? So we will do oh my God, the number line with the -3 and +2, right? And now we check x plus 3, x minus 2 separately, right? Because we have two absolute values. We might have three different intervals here, right? So if we, let's say, use -4, 0, and let's say 3. I don't know if we will be checking that side or not. We don't really need that. Okay, so when we plug in -4 into the first absolute value, we get negative, right? When we plug -4 into the second, we get also negative, right? So negative times negative is positive. So this side, from -infinity to -3, that's gonna be positive, right? So let me put that like that.
But don't you have to do it for the denominator also?
It's not in the absolute value yet, so we are checking only the absolute values.
Oh, I see.
Okay, and then for 0, we have positive, negative, so that's going to be negative. And yeah, the rest we don't need because we are interested in this one, right? So now we would have x plus 3, x minus 2 divide by x plus 3 with the negative sign in front, right? Negative if x is greater than -3, and with the positive of x plus 3, x minus 2 divided by x plus 3, if x is less than -3. And now here you can cancel, and we have negative x minus 2 and positive, oh, sorry, it's not absolute value anymore. And with positive x minus 2, if x is greater than -3 and if x is less than -3. Okay. Yeah, and that's going to be, I believe that's the same. Yeah, it's the same. Okay. So in any case, the limit does not exist because one is going to be positive, another one is going to be negative, or the other way around. And our limit will not exist in this case. Okay. All right, so number 2, what do we have here? Evaluate. Again, limit as x approaches 1 of square root of x minus x squared divided by 1 minus square root of x. Okay? All right. So there are two ways you can do that. First way, okay, so first thing that you need to keep in mind is that if you see this, sorry, not absolute value, the square root, you might want to multiply by the conjugate, or you can maybe apply the difference of squares somewhere, or the difference of cubes or something like that. So look for those things. But first you need to check if the limit even exist or not, right? So we would plug in 1 and we have square root of 1 minus 1 squared, 1 minus square root of 1, which is 0 over 0. So that's indeterminate form, right? So now you need to start manipulating the function to find the limit. So in this case, when you have 0 over 0, you have a limit, but the function is undefined at that limit, at that point. So first case, or first solution you can do is, well, let me rewrite that just as a function. 1 minus square root of x. So what we can do here, now notice that x squared, that's the same thing as square root of x to the fourth power, right? So if we have that, then we have square root of x minus square root of x to the fourth power over 1 minus square root of x, right? So now we can factor out a square root from the numerator, and we will have square root of x 1 minus square root of x to the third power divided by 1 minus square root of x. Now, as you can see, these are somewhat similar, but the only thing is we have a cube here, and remember when you see a cube that it's most likely that you'll need to use a minus b cubed. A cubed minus b cubed, a minus b, a squared plus ab plus b squared, or the positive version of that, right? Okay, so we will use that because 1, it's the same thing as 1 cubed, right? So we can write it as square root of x, 1 minus square root of x, and 1 squared plus 1 times square root of x plus square root of x squared, right? Divided by 1 minus square root of x. Now, as you can see, we can cancel these two, right? And we will have, let me simplify this factor here. So we have square root of x, 1 times 1 plus square root of x plus x, right? So this is what we have. And this, so you would add a limit everywhere, right? It's just, I showed you how to simplify it without applying limit yet, right? So we would have limit as x approaches 1 of square root of x, 1 plus square root of x plus x. And in this case, we have no problem because we have no denominator, right? So we will plug in 1 times 1 plus square root of 1 plus 1, which is just 3, okay? So that's one way. If you like it, you can use this one, or there is another way that is, I think it's more kind of, involved. You would need to multiply. You will need to see what you need to multiply. You will probably need to be more careful. So solution 2, okay? So we have the same limit as x approaches 1 of square root of x minus x squared divided by 1 minus square root of x. So now you see that you have the roots in the numerator and in denominator, and we had a problem like that once in a lecture, and I told you you probably want to multiply by the conjugate of the numerator and also separately by the conjugate of the denominator. So let's multiply. So we would have square root of x plus x squared, right? Top and bottom. So that would be the conjugate for the numerator. And then we simultaneously multiply by the conjugate of the denominator, which is 1 plus square root of x, right? Let me actually make it another color, different color. Okay. So now we will combine these two into one factor and these two into another one, okay? So we would have, for the numerator, we would have x, or if you want, square root of x squared minus x squared squared, right? So that's first one. And this one, we just leave it as it is. So 1 plus square root of x. And for the denominator, we combine these two together and we would have 1 squared minus square root of x squared. That's 1. And another factor, which is this one, we just leave it as it is. We don't do anything with that. Okay, again, you can skip this step and do it in your head if you feel comfortable. That's totally fine with me. But okay, so we let me simplify it. So we will have limit as x approaches 1 of square root of x squared, that's just x, right? And then this x squared squared, that's gonna be x to the 4th power. And we have here, just rewrite the rest. Now in denominator again, 1 squared, that's just 1, minus square root of x squared, that's just x, so minus x, and we rewrite the rest. Now, I want to factor out x from the first factor and see what I get. Okay, so I have limit as x approaches 1, x 1 minus x cubed, and I hope you don't mind if I just duplicate the rest. Okay, so what I did is only manipulated, only factored out from the first factor in the numerator. Now you can see that we have an option to cancel these two, but only after we apply the difference of cubes, right? Because technically this is 1 cubed minus x cubed, right? So you would need to separate that or apply the formula, this formula, right, to this factor, and we can start canceling. So we have limit as x approaches 1 of x. Now 1 minus x, 1 squared plus 1 times x plus x squared, right? And the rest is the same. So we have 1 minus x in the denominator and square root of x plus x squared in the numerator. Okay, so now we can cancel these two, and I think that is that solves the problem with the hole in the denominator. So we would have then just I'll plug in 1 in every x I see. Okay, and I will have 1 times 1 plus 1 plus 1 squared, then 1 plus square root of 1, and in denominator I have square root of 1 plus 1 squared, which is, let me see, 1, 2, 3, 3 times 1, 2, that's 6, divided by 1 plus 1, that's 2, right? So again, we have 3. So that's the same solution that we have in both cases, right? So you choose your own, approach. As you can see, one problem can be solved in different ways, depending on what you are more comfortable, or if you see some, approach right away. So try different things. As long as you apply the formulas correct, everything should be fine. Okay. Next problem. Limit as x approaches 0 of 2 over x square root of 4 plus x minus 1 over x. Okay, so now if we plug in 0, we have 2 over 0 minus 1 over 0, which is essentially infinity minus infinity. That's not the we cannot have that, right? This is unacceptable. So what you need to do first is probably combine these two fractions into one and see what happens. Okay, so we have limit as x approaches 0. Now, the first function has the denominator x square root of 4 plus x, and the second fraction has the denominator of x. So both of them have x. So to have a common denominator, we need to multiply the second fraction by square root of 4 plus x, right? So let me write that. 4 plus x. So we would have here 2 minus 1 times square root of 4 plus x divided by the common denominator now. right? Okay. So now we have that. If we plug in 0, we have 2 minus square root of 4 divided by 0 times 4 plus, yeah. So we have 0 over 0, okay? So again, it's indeterminate form. We need to manipulate the function, right? So we start with probably, again, since we see that there is a square root, uh, and you cannot multiply by the conjugate of the denominator because we have only one term here, right? But in the numerator, you have two terms, so you can multiply by the conjugate of that with the plus sign, right? So we would have limit as x approaches 0 of 2 minus square root of 4 plus x divided by x times 4 plus square 4 plus x under the radical, and then we multiply by the 2 plus 4 plus x under the radical. And now we can combine the terms or these two factors using the difference of squares, and we have limit as x approaches 0 of 4 minus 4 plus x. So now this square root will be just square root squared, which is, just 4 plus x. If you cancel the, so we have essentially this, right? If you cancel your square root and square right away, put the parentheses, because if you don't put parentheses, this positive stays positive, right? But it's not positive, it's negative, right? Because this negative, it will apply, it will be distributed to the positive x to make it negative x, right? So if you don't write this parenthesis, that's going to be a mistake, right? So please either keep parentheses or keep it in this form where you will see that once you lift the radical and square root, this negative sign will also be distributed to this positive. So please keep that in mind. And now we divide by the x square root of 4 plus x times 2 plus square root of 4 plus x. Okay, so this 4 minus 4, that's going to be 0, right? And we have in the numerator, we have now negative x only, right? What we have is x approaches 0, negative x over the denominator. Let me just duplicate it. And again, we can cancel x's, and we have limit as x approaches 0 of negative 1 over square root of 4 plus x, 2 plus square root of 4 plus x. Now I think there will be no problems with the 0 because we have plus everywhere, so it should be a positive value for the denominator. So we plug in 0 into denominator, we have negative 1 times square root of 4 times 2 plus square root of 4, which is negative 1 over, so this is 2, this is 2, this is 2, so 2 plus 2, 4, 8. So we will have, the answer will be negative 1 over 8. Okay? All right, so that's this question. Another question, what was that? 3, now problem 4. Evaluate again. Limit as x approaches 0 of x minus 1, x squared, x plus 4. Okay, so if we plug in 0, we have negative 1 over a 0, right? So we know that there are 3 ways. Either we have positive infinity, negative infinity, or d and e, but we need to check the left side of the limit and the right side of the limit, right? So you can write it on the exam sheet this way, or you can write somewhere on the scratch paper. This part is not kind of official solution, but we have limit as x approaches 0 from the left side. you choose the value that is close to 0, but from the left side, right? So we have some negative 0.001, for example, like that, right? Minus 1, we plug it into the function. We have negative 0.001 squared, negative 0.001 plus 4. And that would be, so all I need is the signs, right? So in the numerator, it's going to be negative. In denominator, this will become positive, and this is also positive. So the total would be negative infinity. So that's our left limit. Now the right limit would be the same, but with the positive from the right side, right? So we have kind of like positive 0, right? So we have 0.001 minus 1, still negative. And then we have 0.001 squared, also positive. And here we have 0.001 plus 4. Again, that's positive. So we have negative and 2 positives in the denominator, so the total is negative. So now you know that you have a limit and your limit is negative infinity, but what I want you to write as the official answer for this question, you can say, since the numerator is negative and denominator is positive and very small, as x approaches 0, the limit becomes very large and negative. So that's why we have negative infinity here, okay? So you need to explain this part in words, because this, well, yeah, technically this all is not considered like an official solution. You can write it in your exam, that's totally fine, but say, explain why you came to this conclusion, okay? All right, so now problem problem 5. Okay, are you guys okay with the epsilon delta definition, or you want to go over one problem?
If you could do one of the quadratic or the cubic ones again, I think I need to see it again. Thank you very much.
Okay, sure. Let's do then prove that limit as x approaches 3 of x cubed equals to 27, something like that. Okay, using the epsilon delta definition. Okay, all right. So what we are essentially proving, right, is we say that for any given epsilon greater than 0, we want to find delta greater than 0 such that if x minus a, right, greater than 0 but less than delta, then f of x minus L is less than epsilon, right? So in our case, if x minus 3, it should be positive, less than delta, then x cubed minus 27 less than epsilon. Okay. So now for this one, let's just apply the difference of cubes, right? So we have 2 factors, because essentially we want in this then side, we want something that is in terms of x plus x minus 3, right? We want to have some factor of x minus 3 in the then statement, right? So we have x cubed minus 27 equals to, that's the same thing as x minus, so 27, that's 3 cubed, right? So we would have x minus 3, and then we have x squared minus plus 3x plus 9, okay? And let's separate it into two absolute values. Squared plus 3x plus 9. Okay. All right. So, and we know for now that this is what is less than epsilon, right? So we have two factors, right? We have some boundary, oops, on this one, but we have no idea what to do with that. So first, let's choose delta to be equal to 1, right? So we want to find the value for delta. Essentially, we want our x minus 3 to be small enough so that this whole expression is true. Okay? The whole of it, of that. Okay? So we choose delta to be equal to 1. Then we have x minus 3 less than 1. Now we lift the absolute value. So we have x minus 3 is greater than negative 1, but smaller than 1, right? So now we add 3 to all three sides. We have here 2x, and here we have 4, right? So this is the upper boundary for our x. Now we plug in this upper bound. So x cannot be greater than this 4. So we can find the upper boundary for this expression if we plug in 4 into this factor, right? So we would have, let me see, if x equals to 4 or less than 4, right? Then we have x squared plus 3x plus 9, which is 16, or yeah, let me, yeah, well, okay. 4 squared plus 3 times 4 plus 9. So that's going to be 16 plus 12 plus 9, which is 20, 30, 37, right? Okay, so this is our boundary for this guy, okay? We can say that it's less than 37. Okay, so now, again, if x cubed minus 27, which is the same thing as x minus 3, well, let me write that in as a step by step. So it's less than epsilon. That's what kind of did our then statement. This is the same thing as x minus 3, x squared plus 3x plus 9 less than epsilon, right? And we have a boundary on this second factor. So we have x minus 3 times 37 less than epsilon. We can divide by 37 both sides, and we have x minus 3 less than epsilon over 37. So now we have this boundary, and this is the same thing as we have here, right? So we can say that let delta be minimum of 1, our first initial guess, right here. And epsilon over 37. You will end up using the term that is in terms of epsilon anyways, but we need to have this initial guess for these cases. And now you can start the proof, right? So now again, given epsilon greater than 0, choose or let delta to be minimum between 1 and epsilon over 37. If x less than 3 less than epsilon, delta, sorry, x minus 3, not less than, x minus 3 less than delta. Now we start going to the then statement, right? So we want to go all the way down to the then statement where we have x cubed minus 27 less than epsilon, right? So we need to get from the top, from the if to the then statement. So now we can say that we can change the delta back to the epsilon over 37. We can multiply both sides by 37. We have 37 x minus 3 less than epsilon. And we know that this 37, that's the upper boundary for our x squared plus 3x plus 9, right? X minus 3. And we can put them into under one absolute value and just combine that. And we have x squared, or we can say x minus 3, x squared plus 3x plus 9. And that's the same as x cubed minus 27, right? Less than epsilon. So we came to our conclusion. So we can say that, therefore, limit as x approaches, what was that approaching? 3? 3 of x cubed equals to 27 by the definition of a limit. Okay, good. Okay, now next question. Problem 6. So let f of x be equal to cosine x if x is less than 0, 0 if x is equal to 0, and then 1 minus x squared if x is greater than 0. What we need to find is where is that? Investigate the continuity. All right. So what does it mean, investigate the continuity? We need to check how the function behaves essentially everywhere, right? We want it to be continuous everywhere. So we need to check all the points essentially. So we know that cosine function is smooth, nice behaving function. It's continuous at least before 0, right? So we have a condition here. If x is less than 0, the function is cosine. So everything is fine, right? So let me just kind of graph as we move along. We don't have to, but let's just, look at what's going on. Let me put it in the middle. So we have 0 here, and let's say 1 here, -1 here. Let's do pi over 2 here, negative pi over 2 here. Oh, we have only negative, right? And then we have pi, negative pi here. So we have cosine x on this side. So, and it goes, normally to the left side. Then we also know, okay, so we have then a point at 0, right? So this point is hollow because we are not including 0 here, but we have a solid point right here at the 0, right? It's going to be 0. And then for the last piece, we have 1 minus x squared. So that's a parabola looking down, and it is also lifted 1 unit up, right? So we have essentially, so we have just a regular parabola, x squared, that is frowning, right? So this is negative x squared, so we don't need that. And we also need to lift it 1 unit up. So that's gonna be somewhere like this, I think. So this is our 1 minus x squared, right? So as you can see, if this point was here, right? It seems like everything would be nice and and continuous. But since we have this discontinuity here, right, and we are not including 0 again for the parabola, we have this removable discontinuity, right? It's not jump, it's not infinite discontinuity, it's removable discontinuity when one point is what's it called, undefined, where we kind of draw a graph, or it's somewhere in other place. But now analytically, how we show that, we need to check. So we said that cosine is a normally behaving function. 1 minus x squared is also continuous everywhere. The only place where we need to check what's happening, if you don't want to draw the graph, and you don't have to, but it's just, oops, it just visually helps to see what's going on with the function. So now let's just check analytically or mathematically what happens around 0. So we need to check limit of f of x as x approaches 0 from the left side, and limit of f of x as x approaches from the right side. And we also need that to be equal to f of 0, right? Okay, so all these three conditions should be met, and they all should be equal to each other, right? In this case, we have a continuity. So from left side, we will be using this function cosine. So we have cosine of x of 0, right? So that's going to be 1. Now from the left side, from the right side, we will be choosing this function 1 minus x squared. So we would have 1 minus 0 squared, which is 1. So these two are fine. But now when we check so you can say that the limit exists, right? The limit is 1, and we see that from the left side we go, and from the right side we go to 1, which is totally fine for the limit to exist. But now for the continuity, we also need to check if f of 0 is also equal to 1. So if it's equal to 1, then we're good, it's continuous. But since we have this third condition right here, right? If x is equal to 0, then the function is equal to 0. So that's going to be 0, which is not equal to what the limit is. So we can say that the function is not discontinuous, not continuous at x equals to 0. Okay, so don't forget to write some kind of conclusion. Okay, don't just leave it like this. I can see the answer, right? But I don't know, so what? So is there discontinuity? Is there continuity? So you need to explicitly say that since these three values, or two values, are not the same, then we have discontinuity somewhere. It would be nice if you write what kind of discontinuity, but if question doesn't ask, then you can skip that. Okay. Next question is problem 7. We have here again, investigate the continuity for the following function, or also, actually, no, not this one. Find the limit for e to the negative 2x sine 3x, okay, as x approaches infinity. Okay, so essentially what it's asking is, what is the limit as x approaches infinity of e to the negative 2x sine 3x? Okay, so in this case, we're not really sure what to do, because if we plug in infinity here, God knows what happens, right? We don't really know what's going on here as well. It's not really clear, right? So we also know that we have this nice theorem, which is called squeeze theorem, that we can apply here to just start with two functions that are kind of like boundaries for one of the functions, right? So we know that sine is bounded by -1 and 1, right? So we can start with that. So we would have sine of x is less than or equal to -1 and 1. And obviously sine 3x is also bounded by the same functions, right? Or the same values. Now we just multiply everything by e to the -2x. So we would have negative e to the -2x less than or equal to e to the -2x sine 3x less than or equal to e to the -2x. And now we just apply the limit. So essentially with all these steps, we are getting closer and closer to our original question, right? So the next step will be, so we're right here, right? This is where we are so far. So now the only thing left to do is just to apply the limit to all three sides. And we have limit as x approaches infinity of negative e to the -2x less than or equal to limit as x approaches infinity of e to the -2x sine 3x less than or equal to limit as x approaches to infinity e to the -2x. Now, if you don't remember how e to the -x looks like, it's not really a problem. What you need to remember is e is just a number, right? And e to any negative value, that's the same thing as e to the 1 over e to that to the positive of that exponent, right? And we know that if this x approaches infinity, right, what happens here? 1 over e to the infinity. So this becomes a really, really large number because e is greater than 1, right? So we would have 1 over a big number. So what do we have at the end? We have 0 here, right? So basically that's all that you need to know or remember. So in this case, we have limit as x approaches infinity of negative e to the -2x. That's the same thing as -1 over e to the 2x, or yeah, as limit goes to, as x goes to infinity. And now in this case, we would have negative, and in denominator, we have a really big value. So the fraction itself becomes a very small value, close to 0. So we have a 0 here, right? It doesn't matter if it's negative or positive. And also for the other side, as x approaches infinity of positive e to the -2x, the same thing. We have limit as x approaches infinity of 1 over e to the 2x, right? Again, if we plug in infinity, we have a really big value in denominator, which gives us a really small value overall, right? For the fraction. So we have 0. So we can say that our limit as x approaches infinity of e to the -2x sine 3x is bounded by 0 from both sides, right? So it has to be 0. So limit of our f of x as x approaches infinity is equal to 0 by squeeze theorem. Okay? So this is a problem on the squeeze theorem. Now I have, I think, 2 more problems. Okay. So let's do problem 8, I think, right? Yes. 8. Okay. Find the values of k and m that will make the function f continuous, that will make the function f continuous everywhere on negative infinity to positive infinity. Okay, so f of x is x squared plus 5 if x is greater than 2, m times x plus 1 plus k if x is between -1 and 2, and 2x cubed plus x plus 7 if x is less than or equal to -1. Okay? So we want it to be continuous, right? So first thing we can see that x squared plus 5 is continuous everywhere except maybe on the critical value where we have the switch from one function to another. So we need to check point x equals 2 or as x approaches 2, right? Now second function, given that m and k are constants, I didn't write that. So find the values of constants k and m. Yeah, so x plus 1. So this whole thing, it's just a line, right? So x to the first power, it's a line. So it also behaves nicely on its interval. So we only need to check -1 and 2, right? And also the third function, everything also looks nice because that's a cubic function. It's continuous everywhere. So the only problematic points that we need to check are at x equals to -1 and at x equals to 2, right? Okay. So first let's start with -1. So at x equals to -1, we have f of -1 is what? So it's f is equal to -1 at this function. So we have 2, we're using 2x cubed plus x plus 7. So we plug in -1. We get 2 times -1 cubed plus -1 plus 7. That's going to be equal to 4, right? Okay. Now, the function defined at this point, f of -1 is equal to 4. Now we need to check if the left and right limit also equal to 4, right? Limit as x approaches -1 from the left side, and limit as x approaches -1 from the right side. So from the left side, we are looking at this function, right? Because that's less than -1, right? So that's the left side. So we will plug it in here. We will use this last function, 2x cubed plus x plus 7. It seems like we will have no problem with just plugging -1 into this function, and we have 2 times -1 cubed. Again, the same thing as when we were evaluating the function. So we have 4, and for the right side, we will be using this function, right? M times x plus 1 plus k. So m plus x plus 1 plus k. So we know that it's supposed to be 4 for a function to be continuous, right? We want to find the values of this k and m for a function to be continuous. So in order for them to be continuous, for the function to be continuous, we need left limit equals to right limit equals to the function defined at that point. So we want it to be equal to 4, right? But before that, let's just plug in -1 to our x. So we have m -1 plus 1 plus k. So that's going to be 0. So we have just k. And so from here, we know that k should be equal to 4, right? So we found our k so that the limit exists, okay? Now, at point, as x approaches 2, we need to check the limits again from the left, from the right, and at the point. So at the point of f of 2, we will be using this function, m times x plus 1 plus k. And now we know that k is 4, so we will use m x plus 1 plus 4, right? Because we found out that k is 4, so we would have m 2 plus 1 plus 4. We have 3m plus 4. So for now, that's it. We cannot do anything else yet. And we see that the left limit will also be the same, right? So we can say limit as x approaches 2 from the left side will again be the same thing. So m x plus 1 plus 4, that's going to be 3m plus 4. But from the right side, we will choose the first function, right? X squared plus 5. So we have limit as x approaches 2 from the right side, x squared plus 5. Let's plug in 2 into our function. We have 2 squared plus 5, which is 9, right? So we know that for a function to be continuous, these values, they should be all the same. So this, and this, they should be the same. So we can equate them. So we can say that 9 should be equal to 3m plus 4. And I'll just solve for m. And we would have 3m equals to 5, m equals to 5 over 3. Okay. So for the values of m equals to 5 over 3 and k equals to 4, this function will be continuous everywhere. Okay? So that's problem 8. Anyone has a question? No? Okay. And now, yeah, and then last problem that I have here is using what's it called? Intermediate value theorem. So problem 10. Does 2 sine x equals to 3 minus 2x has a root on 0 to 1? And we will prove our answer or explain our answer, right? So first thing, we need to define f of x, right? So we will move either 2 sine x to the left side, to the right side, or 3 minus 2x to the right side. Doesn't really matter as long as you define your f, right? So 2 sine x minus 3 plus 2x, that's our function. The domain. So we know that sine is, the domain of sine is all real numbers. And also this is essentially a line, so also all real numbers. So the domain of f of x is also all real numbers, or at least it's definitely it's gonna be continuous. So f of x is continuous on 0 and 1, and this is one of the criterias for the to apply this theorem. Now the second thing that we need to do is we need to evaluate at the endpoints, so f of 0 and f of 1, right? So we would have 2 times sine 0 minus 3 plus 2 times 0, which gives us negative 3. So this is gone, we have negative 3. Now at f of 1, 2 times sine of 1 minus 3 plus 2 times 1, again, use the radian modes for the sine one, and you should have something close to 0.683. Now, our n can be a value, it is a value between negative 3 and 0.683. As long as one of them is negative and another one is positive, right? We're fine. So we can say that n can be 0, so there exists a number C between 0 and 1 such that f of C is equal to 0 by intermediate value theorem. And that would be the solution. Or you can say that so we have, or the function, so f of x has a root on 0 to 1. Okay, so this is essentially what the question was asking. Do we have a root? Yes, we do have a root, because n if eventually it can be 0 because it's between -3 and positive 0.6. So it will definitely cross the x-axis at some point, right? So we have a root there. Okay, so that's I think all I have for you. Do you have any questions? If not, then we can finish with that and you can go back to preparing for exam.
Thank you, Professor.
Thank you, Professor.
Yes, thank you very much, Professor Boyd.
No
Thank you.
problem.
Yep.
Okay.